Welcome to another video of computational thinking and algorithm unit. In this video, we are going to talk about algorithm evaluation and efficiency. Okay, so is it fit for a problem? How is it complexity and optimization and things like that? Okay, so first of all, we are just going to discuss about fitness for a purpose. Simply that means, does this algorithm or does the algorithm that you have created solve the problem that you are just looking for or not? Okay. And for that, we have just gotten some factors, okay? Factors to measure algorithm fitness. The first one is logical reasoning, okay? Does it handle all inputs, normal, boundary, and erroneous data or not, okay? Or does it just give you wrong answers or crash sometimes? So that is very important, okay? The next one is outcome accuracy, okay? Does it consistently lead to an expected outcome or not? Okay, always it should just give you the correct answer. And consistency produces the exact same result every time it is run with identical data sets. Okay, so these three are very important: logical reasoning, outcome accuracy, and consistency. If your algorithm passes these three, then we can say that this algorithm is a fit algorithm for the purpose it is developed for. Then talking about flexibility and extensibility, which is very important for your exams and for your codes. Okay, see, your program has to be able to adapt to different data sets. Okay, so if you are just kind of for example, if you are traversing on a list with something like this, for I is equal to, or for I from 0 up to 20, so that is a fixed one. If the data changes, then this won't work. But if you just say use something like length of the array, okay, length of my array, or just length of array, then here if the length of the array changes, the loop as well changes. Okay, and it just simply works the exact number of times as the amount of data inside the list. Okay, so adapts perfectly to any data set size. So that is very important. While you're coding, your codes have to be just kind of like this. Then measuring efficiency, okay, how good is this algorithm? Many algorithms can solve the same problem. For example, searching algorithms, we studied two, sorting algorithms, we studied two of them, and they are just kind of fit. They do solve the problem, okay? But checking for efficiency or measuring efficiency. So we have gotten two different things that we have to care about when thinking about the efficiency. Okay, one is time efficiency and the second one is space efficiency. Okay, and be careful with time efficiency. We do not mean how many seconds does it take to solve a problem. Okay, because according to many factors like hardware power, or how busy the computer is. Okay, so seconds might change. We just mean how many operations does this algorithm perform or just do to get to the result. Okay, so that is time efficiency, measures the mathematical operations and proceeding time an algorithm requires to finish. Then the second one is space efficiency. It means how much space or how much memory does it use. So space efficiency measures the auxiliary storage and memory overhead required to run the process. Okay, for example, merge sort, we needed extra space, but for bubble sort we did not need. Okay, so these two are very important, and when we are comparing the algorithms, we have to consider both of them. See, efficiency matrices, the things that we are doing, comparisons and passes, how many operations are done, that can be just one thing, or how many times a loop is repeated. Okay, that can also be used to calculate the efficiency. Okay, so the first metric, number of comparisons, how many times the computer evaluates two values against each other, for example, in sorting. Okay, and matrix number two, the number of passes, how many times the algorithm must completely traverse the data set before terminating. Okay, so there can be some matrices while thinking about the time efficiency. Then complexity scenarios. Okay, we have the same algorithm on different data sets can work faster or just slower. Okay, and what can be just the reason there? We can have different scenarios. See, in the best case scenario, for example, in linear search, the best case scenario, for example, the data is in the first element, so only one comparison and there you just found the data. Okay, the worst case scenario, the data that you're looking for is not present there, or it is in the last index. Okay, so you have to compare or just search through the complete array. Okay, so that is best case scenario, that is just minimum execution steps to complete the task in some special scenarios. Then worst case scenario, maximum execution steps, okay, before finishing or failing. In the videos of search algorithms and sort algorithms, we have just discussed about them indirectly, okay, before as well. Then the average case scenario, that is the mathematical middle ground every over many operational runs. So many runs you will just do and you will just take the average of them. The one which is really important is worst case scenario. If we have just created an algorithm that is doable in worst case scenario, so in average and best, obviously that will be executed. Okay, so that's why worst case scenario is very important and we are just always counting that. Search efficiency comparisons, although we have just done this in the unit of search algorithms before. See, linear search and binary search. Linear search is brute force and binary search is divide and conquer. And the prerequisites, linear search does not have any prerequisites, can work on both sorted and unsorted data, but in binary search data must be sorted. Best case scenario in both of them, one comparison. Okay, data is just in the first element for linear search, that is the best case scenario, and data is in the first median, exactly the middle. Okay, so that is the best case scenario for binary search. In the worst case scenario, linear search performs n comparisons while binary search performs around log n comparisons. Okay, see, levels of efficiency, the algorithm that we have studied yet. Okay, for example, we studied binary search. Binary search was from the level log n, okay, big O of log n, logarithmic. So this is highly efficient for massive data sets. See the number of data size, or just the data size, how much it is increasing. The number of executions or the steps are not increasing that fast. So this is very good. Okay, then after that, yeah, we have gotten linear on or big O of n. Okay, so here the same amount the data increases, the same amount the number of operations increase. Okay, so that is linear. And after that, yeah, we have gotten n log n merge sort. Okay, that is just a little bit slower than linear, but again, just for many algorithms that is quite good. Okay, for example, for sorting, this is quite nice. And bubble sort, that is n to the power of 2, okay, or n square. So this is kind of slow for big data. Okay, as you can see, the number of data increases slowly, but according to that, or compared to that, the number of executions or the work it does increases a lot. Okay, so this becomes much more slow. So think about this by yourself as well. Okay, and if there is any kind of questions, you may just put your questions in the comment section. Sorting trade-offs. Okay, so balancing time versus memory. So again, comparing bubble sort and merge sort. Okay, so bubble sort, as we just talked, it takes a lot of time, but memory usage of this is constant. It performs the operation in place. Okay, so it does not create copies of data. So high space efficiency but poor time efficiency. Okay, it's brute force and it's slow. But merge sort, on the other hand, okay, it has high time efficiency. In time efficiency, it's good. For large data set, it works quite nice, but poor space efficiency. Okay, it has memory overhead, so due to copying sublists recursively. Okay, so that is what you have to just know. Then some tips for exam. In your exams, do not forget the technical justifications and just using the terminologies nicely. Okay, always use the exact or true terminologies. For example, brute force, memory overhead, divide and conquer, things like that. Okay, if you do not use these words exactly, you might lose numbers in many questions. Okay, then if a large list is searched only once, linear search is better. Okay, there is a very large list and you need to just perform search on that once, so go with linear search. Okay, but yeah, if a lot of search will happen there, then you can just first sort it, then after that work with linear search, so that will be just kind of better. But sorting itself needs a lot of time and itself just performs a lot of things, and if you have gotten only one search on a data, really it's not worth it to just make the sorting first with n log n, then after that, yeah, perform the operation or the search operation only once with log n. Okay, instead of that, just at once perform n. Okay, linear search with big O of n. And precision in definition. Okay, so provide clear structural definitions, not just vague purposes. So remember that. Okay, build on the scenario provided in the prompt. For example, in the prompt, if the text says the list is sorted, use that detail in your justifications. Okay, so that is just very important. Some example questions. Okay, state the three factors used to measure algorithm fitness or efficiency. So yeah, that is logical reasoning, outcome accuracy, and consistency. Question number 2, calculate the maximum number of comparison a linear search performs on a list of 50 items. So in worst case scenario, we have just gotten big O of n. Okay, so if 50 items, then we have gotten 50 comparison. Identify which sort is most efficient for a data set of 500,000 items and justify using technical terms. Okay, so merge sort is better. It uses a divide and conquer strategy, which scales significantly better than a brute force or bubble sort, despite carrying a memory overhead. See, I'm just using some technical words here. Okay, divide and conquer, brute force, memory overhead. So that they are just very important. That's it. Wish you all the best for your exams. Okay, and for your preparation. Do not forget to like and subscribe our channel. See you. Good luck. Goodbye. Keep growing. Keep shining.